As of this week in May 2026, the summit of Iran's Taftan Volcano has not subsided by a single measurable millimeter since the confirmed ground uplift that began in July 2023, meaning the pressurized system identified by researchers from the Spanish National Research Council and published in Geophysical Research Letters is still holding, still sealed, still accumulating somewhere between 490 and 630 meters beneath a 13,000-foot peak that has not erupted in recorded human history, in a province where there is not one permanent GPS receiver, not one seismometer, and not one continuous gas analyzer watching. What happens next? If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources: the Smithsonian Global Volcanism Program, the European Space Agency's Sentinel-1 satellite mission, peer-reviewed research in geophysical research letters, USGS seismic records, UNESCO's Intergovernmental Oceanographic Commission, and published work from the Spanish National Research Council's Institute of Natural Products and Agrobiology. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are public. The data is accessible. The responsibility to check belongs to all of us, but that is not even the complete picture. What the satellite data captured between July 2023 and May 2024 is a surface signal 9 centimeters of ground rise near the summit of a volcano that geologists had, until that moment, largely categorized as a relic of prehistoric Earth, 3.5 inches. You press your fingers together and measure the width of your hand from thumb to pinky. That is roughly what the summit of Taftan moved upward in 10 months. But what moved was not the surface of a garden, not the settling of loose soil after a rain. What moved was the top of an andesitic stratovolcano with a crustal thickness beneath it of approximately 60 kilometers, nearly 37 miles of stacked rock rising under pressure from a hydrothermal system whose source has been geodetically modeled at between 490 and 630 meters below the summit, fed from a magma reservoir sitting more than 5 kilometers below that. The surface signal is the visible edge of something far older and far larger than the measurement suggests, and the measurement has not reversed. The ground has not sunk back. The pressure, as of the most recent satellite assessments, has not bled off. What this means, and scientists choose their language carefully here, and that careful language is itself the warning, is that the system is not inactive. It is accumulating. Taftan stands at 3,940 meters above sea level, between 12,795 and 13,000 feet depending on the summit measured. The twin peaks of Narka and Mataku, separated by a saddle 1 2/10 kilometers wide in Iran's Sistan and Baluchistan province, near the border with Pakistan, in Persian and Balochi. The word Taftan translates roughly as blistering, smoldering, fuming. The people who named this mountain did not choose that word by accident. The volcano releases water vapor, carbon dioxide, hydrogen sulfide, hydrogen fluoride, and approximately 20 tons of sulfur dioxide every single day from its fumarolic vents. Active gas release is visible from a great distance, producing a white plume that under the right atmospheric conditions can be seen 100 kilometers away. This is not a dormant system in any casual sense of the word. It vents constantly. It breathes. What changed between 2020, when PhD student Mohammed Hassan Mohammednia first analyzed Sentinel-1 satellite imagery and found nothing alarming, and 2023, when the same researcher returned to the data after residents of Kash began reporting intensified sulfur odors detectable 50 kilometers away, is that the mountain had begun to breathe differently. The city of Kash sits approximately 45 kilometers south of Taftan's summit. Population estimates place it between 80,000 and 100,000 people. These are families who live in a desert landscape at the edge of one of the most geologically active subduction systems on Earth, in a province that Iran's own government has historically underserved in terms of infrastructure, scientific monitoring, and disaster preparedness. In the spring of 2024, residents of Kash did not need a satellite to know something had changed. They could smell it. The rotten egg sharpness of hydrogen sulfide, the choking chemical edge of sulfur dioxide, these are not abstract readings on a gas spectrometer. These are smells that burn the inside of the nose and the back of the throat. Local reports documented hospitalizations in Kash for allergic reactions triggered by the sulfur emissions. The governor of the Taftan region, Alireza Shanavazan, acknowledged publicly that activity was higher than in previous years. He described it as seasonal, tied to snowmelt and rain. What he did not have access to, because no one in the region had the instruments to measure it, was the data that satellite radar had been quietly collecting from 700 kilometers above the planet's surface. The ground was moving up, not seasonally, not from rainfall. The researchers filtered the INSAR data specifically to remove atmospheric noise caused by moisture and temperature. They filtered for earthquakes. They confirmed that neither rainfall in this arid region nor any seismic event in the vicinity triggered the uplift. The source was internal. Something beneath Taftan was pushing upward, and it was doing it on its own terms. Here is where this account becomes genuinely significant. The model that emerges from the data places the pressure source, a shallow, pressurized hydrothermal system, blue-coded in the researcher's schematic, at 490 to 630 meters below the summit, capped by layers of dynamic permeability. Below that sits the deeper magmatic system, the Mush Reservoir, at depths of 3.5 29 kilometers. The current interpretation, held by the team led by Pablo of the Spanish National Research Council, is that the uplift was most likely caused by one of two processes. Either the permeability of rock within the shallow hydrothermal zone changed, trapping gases that had previously been escaping and building pressure in rock pores and fractures, or a small undetected movement of magma from depth released volatile gases upward into the hydrothermal zone, raising pore pressure and causing the ground to heave. The researchers cannot yet say which. What they can say with the confidence that satellite geodesy and pressure source modeling allow is that the deformation matches a shallow source at the measured depth. It was internally driven, and the absence of post-unrest subsidence as of the most recent assessments suggests the system remains pressurized. The pressure has a route out. The question is which route it chooses, and when Taftan is the most prominent center of the Makran volcanic arc, a chain of volcanoes stretching approximately 450 kilometers along the Arabian-Eurasian plate boundary. This is not a distant or abstract tectonic feature. It is the boundary where the oceanic portion of the Arabian plate has been descending beneath the continental mass of Eurasia since the Cretaceous period, more than 65 million years of subduction, with convergence rates measured by GPS at between 23 and 27 millimeters per year, 23 to 27 millimeters per year. That number sounds small. It is not small. It is the same category of convergence that built the volcanic chains of the Pacific, that constructed the Cascades, that built Pinatubo in the Philippines before it erupted in 1991 with enough to lower global temperatures by 0.5 degree Celsius for more than a year. The Makran subduction zone is one of the largest accretionary prisms on Earth, a vast wedge of compressed sediment driven up by the plate collision, and it is not finished. The plates are still moving. The pressure is still building. Taftan sits directly above the point where that subducted Arabian oceanic crust, descending at a low angle of approximately 13 degrees, begins to release its water into the rock above, generating the conditions from which magma is born, and the geological record holds the evidence that this system is capable of more than fumaroles and ground deformation. The most recently dated volcanic materials at Taftan carry a radiometric age of approximately 710,000 years, 71 million years, confirmed by laboratory dating. That is the number that defined the volcano's status as extinct in scientific literature until October 2025, when the Geophysical Research Letters paper by Mohammadnia and their team unambiguously their word documented volcanic unrest. The reclassification that followed was not a minor administrative adjustment, it was a fundamental revision of risk. A volcano classified as extinct carries no emergency preparedness requirement, no evacuation planning, no monitoring obligation. When a volcano is reclassified as dormant, these obligations become real. They become urgent. Taftan has been reclassified. As of this spring in 2026, there are still no permanent GPS receivers. On its slopes, there are still no seismometers. There are still no continuous gas analyzers. The Sentinel-1 satellite constellation, part of the European Space Agency's Copernicus program, remains the primary observational tool, with a revisit cycle of approximately 6 days. 6 days between data points, on a system that researchers have described as requiring immediate attention. This is not a hypothesis. This is documented in the geological record, and the record of it is still preserved in the rock. But to understand what the geological record truly warns, it is necessary to travel not to Taftan's own uncertain history, but to the broader system in which it sits, the Makran subduction zone, and to the morning of November 28, 1945, at 4:06 in the morning, local time, a magnitude 8. One earthquake ruptured along the Makran subduction zone approximately 97.6 kilometers south-southwest of Pasni on the coast of what is now Pakistan. The rupture extended beneath the seabed across hundreds of kilometers. The shaking lasted approximately 30 seconds. It was felt as far away as Calcutta, now Kolkata, more than 2,000 kilometers to the east, and then the sea moved. The tsunami that followed struck the entire Makran coastal region. At Pasni and Ormara, the towns were reportedly underwater. At Ormara, the water inundated 5 kilometers inland, destroying 60% of the existing structures. The fishing village of Kudi, 48 kilometers west of Karachi, was erased entirely. Its entire population swept into the Arabian Sea. Death toll estimates in the historical record range from 300 confirmed to as many as 4,000 people across Iran, Pakistan, India, and Oman. Wave heights at some Makran fishing ports reached 12 meters, nearly 40 feet. The tsunami registered at tide gauges as far away as Bombay, now Mumbai. A lighthouse at Manora, 300 kilometers from the epicenter, had mercury spilled from its precision optical mechanism by the seismic waves before the water even arrived. The 1945 event is documented. The death toll is in the record. The wave heights are in the sediment layers, and it has already happened. The question is not whether the Makran subduction zone is capable of generating a tsunamigenic earthquake at magnitude 8. One or above it has demonstrated that capacity. The question the 1945 record forces onto the present moment is this. With coastal populations vastly larger today than they were 81 years ago, with Kash at roughly 100,000 people, with Zahedan, the provincial capital of Sistan, and Baluchistan at approximately 500,000 people, roughly 100 Kilometers from Taftan's summit, with the border town of Taftan on the Pakistani side at approximately 18,500 residents only 100 kilometers to the northeast, with all of these people living in the shadow of a system that is demonstrably active and demonstrably unmonitored. What is the price of the delay in establishing a monitoring network? Think about what life looks like in cash on an ordinary morning in May 2026. The air comes in from the desert to the west, the sun rises over the Makran range, a white plume is visible on the horizon to the north, rising from the twin summits of Taftan, the same plume that has been visible from this distance for generations. Children walk to school past walls of pale stone, the market opens. The smell of sulfur is familiar here, seasonal, the governor has said, tied to the snowmelt. What the people of Cache do not have, and what the researchers have explicitly and urgently requested be provided, is a seismometer that would tell them if the pattern of microseismic events beneath the summit is changing. They do not have a GPS receiver that would tell them if the ground is moving again. They do not have a gas analyzer that would measure whether the sulfur dioxide flux, currently averaging approximately 20 tons per day, is rising toward the threshold where pressure within the hydrothermal cap is approaching critical. They have the smell, they have the visible plume, and they have a satellite passing overhead every 6 days, whose data requires weeks of analysis by researchers working in Spain and the United States before it can tell anyone whether the mountain is behaving differently than it was the last time anyone looked. The connected systems here are multiple, and the science that links them is not speculative, it is structural. The Makran subduction zone, as noted in peer-reviewed geological assessments, is seismically asymmetric. Its eastern segment is the more seismically active portion, with documented historical earthquakes. Its western segment, where Taftan sits, has historically shown lower seismicity, but lower seismicity in a subduction system does not mean lower stress accumulation. In subduction mechanics, areas of apparent quiet can represent zones of locked coupling sections of the plate boundary where the plates are grinding against each other without slipping incrementally, meaning that stress accumulates without releasing in the small regular earthquakes that would otherwise bleed it off gradually. When a locked zone eventually releases, the energy it has stored is proportional to the time it has been locked and the convergence rate at which stress has been fed into the system, at 23 to 27 millimeters of convergence per year, and with decades between significant seismic events in the western Makran, the arithmetic of accumulated stress is not reassuring. There is a second connection the verified science demands be acknowledged. Taftan's hydrothermal system is not isolated from the regional tectonic stress field. Hydrothermal systems are sensitive to pressure changes in the rock around them. A sufficiently large seismic event on the Makran fault system could alter the permeability of the cracks and channels through which Taftan's hydrothermal fluids move, either releasing pressure rapidly and triggering a steam-driven phreatic eruption, or compressing those channels and forcing fluids into new pathways that generate new surface deformation. This is not a theoretical pathway. Comparable hydrothermal systems at Azuma volcano in Japan produced approximately 6 centimeters of uplift from a source at 1.3 kilometers depth before elevated degassing was observed. At La Fossa caldera on Volcano Island in Italy, 6 centimeters of uplift over 3 months from a source, approximately 0.6 kilometers deep, was followed by intense degassing and ground cracking. No eruption, but genuine unrest with observable consequences. Taftan's uplift 9 centimeters, measured over 10 months, from a source at 0.4920, 63 kilometers depth, is slightly larger and slightly slower than either of those events. The researchers classify it within the same category, non-eruptive hydrothermal inflation that is real, that is significant, and that demands monitoring precisely because the outcome has not yet been determined. A phreatic eruption, a steam-driven explosive event, requires no fresh magma at the surface. It requires only that trapped hydrothermal fluids encounter a sudden pathway to release, expanding violently as water flash boils into vapor in the context of rapidly reduced pressure. Phreatic eruptions can be extraordinarily violent, can produce ash plumes, ballistic projectile hazards, and pyroclastic density currents driven by superheated steam. The 2014 eruption of Taftan Volcano in Japan, which killed 63 people with no warning in the middle of a clear autumn day, was a phreatic event triggered by a hydrothermal system that had not erupted in historical times. Monitoring was inadequate. Warning time was 0. This is not presented here as a prediction of what will happen at Taftan. It is presented as the documented category of event that a pressurized, unmonitored, shallow hydrothermal system can produce when the pressure finds a rapid route to release. Now consider what the absence of monitoring infrastructure means in a region like Sistan and Baluchistan in the spring of 2026. The province is remote. The terrain is difficult. The security environment, with insurgent activity documented along cross-border smuggling routes in the Makran range, complicates field deployment of monitoring equipment. The economic pressures on Iran's government in 2025 and into 2026, with inflation rates reported by Iran's State Statistics Center at 42% in December 2025, mean that allocating resources to a volcano that has not erupted in recorded history requires a political will that is difficult to generate in a crisis environment. The researchers who published in Geophysical Research Letters understand this. E's statement was precise and measured. It is a wake-up call to the authorities in the region in Iran to designate some resources to look at this, not a declaration of imminent disaster, a call for attention. The kind of call that, when it is answered in time, means a monitoring network catches the early signals of escalation and provides the weeks or months of warning that allow populations to move out of harm's way. The kind of call that, when it is not answered in time, means the first warning a community receives is the eruption itself. What would the consequences of an eruptive event at Taftan look like, measured against the human geography of the region? The Smithsonian Global Volcanism Program lists uncertain eruption reports from January 1902, smoke observed for several days with strong nighttime glow, and from April 1993, when the Islamic Republic News Agency reported a lava flow traveling approximately 60 meters downslope from the southeastern crater. Both events are classified as uncertain in the official record. Neither caused documented casualties because both were small and both occurred on a mountain whose flanks were not densely inhabited. The geometry of risk has changed. Zahedan, the provincial capital of Sistan and Baluchistan, holds a population of approximately 500,000 people and lies roughly 100 kilometers north-northwest of Taftan's summit. Under unfavorable wind conditions, with the prevailing winds shifting northward, an ash plume from a volcanic event at Taftan could blanket Zahedan within hours. Ashfall of even a few centimeters can collapse weak structures, contaminate open water supplies, destroy crops across entire agricultural regions, ground air transport, and trigger respiratory crises in populations that have no stockpile of protective equipment and no warning that the ash is coming until it is already falling. Across the border in Pakistan, the town of Taftan sits approximately 100 kilometers to the northeast, a community of approximately 18,500 people in Pakistan's Baluchistan province, living on the other side of the same international boundary that separates the two countries' monitoring responsibilities and complicates any coordinated emergency response. Think again about those 500,000 people in Zahedan on a normal morning. The market district near the central square opens at dawn. Truck drivers move goods along the highway that connects this isolated provincial capital to the rest of Iran. Students at the University of Sistan and Baluchistan walk between buildings under a sky that, on a clear day, shows the white plume of Taftan rising on the southern horizon. They have lived their entire lives with that plume. It is part of the visual grammar of their landscape. What no one in Zahedan currently has is a real-time alert that would tell them whether the sulfur dioxide flux from that plume has doubled in the last 24 hours, whether the summit ground has begun to rise again after a period of stability, or whether a cluster of small earthquakes 500 meters below the summit, the kind that seismometers would detect and characterize but that do not exist at Taftan, has begun to appear in the data. The monitoring is not in place, and detection of escalation, while theoretically possible through satellite revisit cycles, is not happening in anything close to real time. The science cannot tell us, with any precision available on Earth in May 2026, whether Taftan will produce a phreatic steam explosion in the next month, or the next year, or the next century. That is not a failure of science, it is an honest statement of what prediction requires versus what the available instruments can provide. A mature monitoring network, GPS units capable of tracking millimeter-scale ground motion in real time, seismometers capable of cataloging the micro-earthquake swarms that typically precede volcanic unrest, gas spectrometers measuring sulfur dioxide, carbon dioxide, and water vapor continuously from fixed positions on the summit. And flanks would not eliminate uncertainty. No instrument on Earth eliminates volcanic uncertainty. But it would compress the uncertainty dramatically. It would convert weeks of satellite processing latency in 2 hours of ground-based data. It would allow volcanologists to track whether the pressure source identified at 490 to 630 meters depth is growing, stabilizing, or beginning to find new pathways. It would provide, for the 500,000 people of Zahedan and the 100,000 people of Kash, the one thing that turns a potential catastrophe into a managed risk: time. S research team has called for exactly this. Their geophysical research letters paper is explicit. Establish monitoring networks, update hazard maps, prepare community-level mitigation plans. The Sentinel-1 satellite constellation will continue to pass over Taftan every 6 days, INSAR data will continue to accumulate. New advances in common mode filtering, the same technique Mohammedania developed to detect the 9-centimeter uplift that previous methods had missed, will improve the ability to extract subtle signals from noisy data. The global community of volcanologists watching unmonitored systems through satellite radar is growing. The tools are improving. The knowledge is expanding. What is not expanding at the required pace is the on-the-ground infrastructure that would give early warning to the people who live beneath the mountain, in the city where the sulfur smell drifts in from the south on warm days, in the border town that shares its name with the volcano, in the provincial capital whose 500,000 residents have never been asked to consider whether their proximity to a reawakened hydrothermal system should factor into their emergency planning. The system is not inactive, it is accumulating, the ground has not subsided, the pressure remains. And somewhere between 490 and 630 meters beneath the twin summits of a 13,000-foot stratovolcano in the southeastern corner of Iran, and rock that has been under pressure for longer than our civilization has existed, fed by the slow grinding descent of an oceanic plate that has been sliding beneath the Eurasian continent since before the first human ancestor stood upright on the African savanna. The pressure is waiting, as it has always waited, for the moment when the rock above it can no longer hold. The youngest dated volcanic material from Taftan carries a radiometric age of 710,000 years. The humans who exist beneath it have been here, in any modern sense of civilization, for perhaps 10,000. The planet does not keep human time. It does not consult emergency preparedness plans. It does not wait for monitoring networks to be installed. The signal the Sentinel-1 satellite captured in those 10 months between July 2023 and May 2024, 9 centimeters of ground moving upward from a source 500 meters below the surface of a mountain that no living person has ever seen erupt, is the same kind of signal that precedes events whose names later appear in the catalogs of historical disasters, pressed into the rock like a signature, preserved in sediment layers that tsunami researchers decode with coarse amples and optically stimulated luminescence dating, long after the wave has receded and the count of the dead has been argued over for decades. The mountain has given its signal. It gave it nearly 2 years ago. The signal has not been recalled. Share.